Okay, now we're recording. So there's just some things, right? So this video, right, it's really important because it just shows you everything you have to do, right? The manual, I think it's pretty good shape now, but the video is me doing it, right? So, and there's this sample file that has everything in there that you need. This is unextracted. So the LT Spice files, all the Python files, and even there's a, it's just easier to show you that if you go into, you have to, download and extract that file, right? But if you go to home, load, and navigate, there's a file with all the settings, right? It's an INI file, right? Configurations, and it's just called SROP37. That's just, now if you, but the manual will show you set the power supplies to, I was actually playing with it this morning to see what else I could study, plus or minus 5 volts, right? But everything is there. All the Python code is there. Okay, so yeah, you start, here is the actual stochastic resonance circuit. And what's great about it is we can do one simulation and get the full width half maximum out of this circuit because there's no forcing function. And we can get the signal to noise ratio out of this circuit because there is a forcing function. In that video, I really explain all of that, right? And yeah, when you have to make sure to change these paths, otherwise you'll get garbage. And you can start getting things like this peak to that without it, and that's the signal to noise ratio. Now here is all the Python. Here's my circuit. What I like about this picture is you can kind of see every hole where everything is. You can, it would be nice if this was a little better focused, but you can see that that's the 100K, that's the 10K, all of these are here. That's all on a line. This is the W2 channel and the W1 channel and the oscilloscope probe and the negative and power supply and the other channel there, right? So yeah, you just turn it on and you have to make sure you have the right hysteresis width, and that's with a triangle wave, right? You just set it up and you just measure each side of it to make sure you've got the right hysteresis width. For me, it was 0.84, but you'll have, variance in your resistors. And what happens is, notice how it's going to 4 volts and -4 and change. That will change from circuit to chip to chip as well. All right. So anyway, I really just want to orient you to things that aren't in that video, and it, or just reinforce that if I'm going to, let's see, what was I looking at? So if I go back to, like, an important thing is when you come to do the noise source, whenever you come back to it, it changes the frequency to 10 megahertz, the sample rate. So you've always got to bring that back to 50 kilohertz. Otherwise, it's not going to work. And then when you're actually doing the experiments, you don't need your XY. Now you can't see what's going on here because the noise is scaled too large, okay? But now you can see that the circuit is switching, right? And you just have to come here, export, and click on this one, all right? And Just run it. Now this plot is there to kind of show you, am I actually plotting the right transient? Am I actually getting anything that makes sense? Right? And this doesn't make sense because there is no forcing function, even though it says it's there. I had turned it off. So it's the same file, right? You're getting the full width half maximum without the forcing function, and then the signal to noise ratio width. So if I go back and go to the signal generator, channel 2, there's my waveform, right? Re-export it. Rerun it, I should now see something with a sine wave in there. Okay, and there's a nice peak at a kilohertz with a signal to noise ratio of 5.9. And that's my input noise RMS. Now, the thing is this is a noisy measurement, and you will get a slightly different values each time you do it. So if I just go back and change nothing, right, and re-export it, I should get slightly different values. Of course, it made a liar out of me, and it's working perfectly today. But sometimes the noise it's random, and like I think I can. All right, now I'm at. You see how it's kind of bouncing around on the screen. Now I should be able to export it. I should get more data, but it might to analyze. But I might get a slightly different value. Actually, got a large, because I took 5 milliseconds of data instead of 1. I actually get more data to average out, and I'm getting a better signal to noise ratio. All right. So I think I just need to take a little bit of time and talk about kind of what's maybe going on. All right. Is that, if I had a perfect sine wave with no noise added to it, I'd get this in frequency. So if this was 1 kilohertz, right, I'd get this one peak at 1 kilohertz. All right. So all these other peaks that we're seeing are really noise. And here's the thing, if I had a machine, there's machines that do this, right? And they sweep it and they average it. You'd see these peaks kind of bouncing around in time. And even this bouncing around in time, but it would be the most solid signal. Now, here's the thing, looking at this, right, you can't really see, you can kind of see a pattern to it, that it's kind of tight, kind of loose, tight, loose, tight, loose, right? But you really need to put it through this power spectral density tool, which is very similar to the FFT, or Fourier transform tool, right? Where it just converts time data into the frequency data, right? But something else is it might be a bit weird to hear it, but let's say we were going from 0 to 10 kilohertz. That power spectral density function will take that noise and kind of smooth it out to give you an idea of what the shape of that noise is, right? So it'll average it out so that you're getting a smooth curve. And that's what as I take that data and I extract, I just curve fit to this pattern, all right? So, I'm going to turn off I'm going to set the channel 2 to constant. So now there's no forcing function. Now I can try to measure full width half maximum. Okay. Okay. So all this is just noise at each frequency bouncing around, right? But I'm extracting a full width, I'm extracting a Cauchy curve to it, right? So that I will always measure the signal to noise ratio based on this curve here, this point. All right, so that I'll take the peak and I'll take its relationship to the curve. And you can kind of see that curve, right? The full width half maximum is without the noise, right? But when you're taking the measurement, it actually extracts the curve again when there is a forcing function, and it takes this point, automatically finds it, and divides it by whatever the curve is right there. All right. Now, these distributions, so this might be the hard part to understand, but when you take these operations, that you actually get negative frequency as well. All right. That's a little bit more than I want to go in today, but this is looking like the bell curve, right? And so you would have, bell curves have standard deviations and the mean and things like that. The thing we're actually measuring, right, is full width half maximum. So what's the width? And we're not actually taking, we're just going from here to here. But if this is 1, what's the width at 0.5? That's all we're doing is, because this is related to the Kramer's rate. So anyway, this shows you how to go through once, right? And then you're going to do like one of the first things in research is trying to repeat the work of others. So you're going to go and make a table here, right? With the same, now, when I say with the same noise values, you might put in this noise amplitude scale factor, right? Let's go back to the signal generator and go to channel 1, the buffer. Notice, oh no, it kept it at 50 kilohertz. This is the amplitude scale factor 1, which will relate to an RMS value, right? So you'll enter in 1, 1.25, and so on. Your theta, your RMS of the noise might be a little bit different, right? And then your full width half maximum might be more different because of variations in the resistors and chip to chip, right? But if everybody repeated this with different chips and, we're all using the same nominal value resistors, but they'll be different, right? We could, I think there's 30 people right now. We'd have 30 sets of data to see just how reliable this thing was, right? So you go through and you set the noise scale factor and then measure these two things, right? Don't try to get your RMS to be exactly what mine is, because that you'll drive yourself crazy. All right. So you just change the noise amplitude scale factor, measure these two things, right? And this is the important part, that one you do without with the forcing function off, right? So I would come back to Scopy, signal generator. So the noise, I'm changing this value here, but channel 2, all you got to do is keep it constant at a 0, right? So you fill out that table, right? Then you do the same thing, but with the forcing function. So once you did that table, you'd repeat everything. With 200 millivolts peak to peak, 1 kilohertz sine wave, okay? And do this table, right? Now, even here's the thing, you'll notice I have one here and one here, and I'm not getting the same noise, all right? It's close, but it bounces around a bit, all right? Then what you'll do is take that data and edit another Python code, which is very similar to the Python plot you did on day 2, right? You just cut and paste the data in here, make sure it's got commas, right? And then you'll run it and you'll get something like this. This was for a different model, by the way. But the important thing is this is the log of full width half maximum versus 1 over theta. And you can extract something here. I'll tell you what it is later. So when you get a curve like this where it's linear and then it kind of drops off, yeah, that you're kind of seeing stochastic resonance. And when the stochastic resonance starts low, has a peak and goes back down versus the input noise, right? That means you're probably really seeing something. Now the curve, so I did the same thing and I got this. And in here, there's these data points that don't make sense. And yeah, I was not getting reliable data, but it was real. And you can tell that, yeah, there's a peak, and then, it was kind of having a hard time. But this, again, that's real data. And it's actually looks pretty linear on that log scale. And what you do is you just cut and paste the theta values and the full width half maximum values, calculate 1 over theta, and then natural log of full width half maximum, do a plot, and then do a linear regression, which you can do any way you feel like. That's just the way I happen to do it. And when I do that, you get a barrier height of 0.705, all right, which is similar to, if we looked at the actual quartic model, that differential equation I showed you, it would be this. The Schmidt trigger doesn't really have that shape, but it does have a barrier height. So the fact that we can extract a barrier height, right, means that yes, we're seeing stochastic resonance. Because the thing about this stochastic resonance is it can take you a while to recognize what it is, right? So something I wanted to show you of like when things aren't working, which I probably didn't show in the video, is let's keep that waveform on, or no, we'll keep channel 2 off, and I'm going to bring the noise peak to 50 millivolts. And I'm going to set my power supplies back to what you'll start it. And notice it's not changing. The output isn't changing because the noise is just too small to get it to switch states. So if you see it not changing, well, of course, something could be wrong, disconnected or whatever. But I mean, just, what does not having the power supplies look like? Right? Just kind of everything zero, right? But even when I enable the power supplies, it's not enough to get this going back and forth. All right, so I think even 0.7 wasn't working. I think I tried 0.9. Oh. $700 millis not working. Still not working. There we go. We're getting something now. Now the other side is what can happen is your peak to peak input might just be causing it to you're getting a peak, but it's your the sine wave is so large that it's making it trip according to the sine wave, and the noise isn't assisting it, right? So if I export this, so it looks like, wow, signal to noise ratio almost 20, right? You can hardly see the noise, but we're actually just getting a square wave because we're putting a sine wave into a Schmidt trigger, and the sine wave is just really big. How can I tell it's a square wave? Is that I have a peak at 1 kilohertz, then I have another peak at 3 kilohertz, and then another peak at 5 kilohertz, and that is a classical shape of a 50% duty cycle wave. Now, if the stochastic resonance was working really well, right, it might do that, right? But the peak to peak has to be less than the hysteresis width. Otherwise, you're not really getting stochastic resonance. All right. So really what you're going to do for your research project is each group will get a frequency. So everybody needs to repeat this. Then each group will get a frequency, right? And then you'll repeat, everyone will do the same frequency, and you'll combine your data into kind of one graph at the end. Okay. Where you'll have basically these will let's say there's 5 teammates, right? There'll be 5 5 of these curves, right? And it'll just be student 1, there'll be a legend, student 1, student 2, student 3. There'll be 5 of these curves, student 1, student 2, student 3, right? And there'll be, and then we can take the average of the barrier height and things like that, okay? Yeah, so tomorrow I'm gonna be kind of engaged in another thing, all right? So I might not be, so we're not meeting anyway, but really work with your TAs first, okay? And yeah, after 5, I'll be available again, all right? But this is where, you know, you're all doing it, and you'll actually be generating real research data. Essentially, you know, how reliable is this circuit from circuit to circuit? Do you know what I'm saying? Is that we'll build it 30 times, and do we get, you know, what results do we get? Okay. Any questions? Because I want to get you to your TAs. Alrighty, so I'm going to end this meeting, and then try to all just check in with your TA right now. Some have class, some will, but, and then you have your meeting times. All right. Don't hesitate to email me. I hope you had a good weekend, and just, you know, actually you're doing the research today. When you repeat that result, you'll be doing research. And then tomorrow you'll be working on the group part, right? And then you'll be writing it up for a talk on Friday. But this is, you really kind of made it. Okay. All right. Take care, everybody. I'll let you go.
Thank you.
Thank you, guys. Let's see. Where is? Oh my.